Good afternoon, dear participants. Can I ask you to kindly take your seats? I'd like to welcome to the podium Professor Paul Richards, who is going to deliver the technical keynote of the symposium on verifying nuclear tests, a historical perspective. Professor Richards, who's originally from the UK, has been living and working in the United States since the 1960s. He has a background in mathematics and became a seismologist and started his science research career on wave equations, the physics of earthquakes, and studies of the Earth's interior structure. He has taught at Columbia University since 1971. Since the early 1980s, he has especially worked on methods to detect and interpret nuclear test explosions, and also worked with the US government's Arms Control and Disarmament Agency, including in the context of the CTBT negotiations in the early 1990s. Amongst his many accolades, he was elected a Fellow of the American Academy of Arts and Sciences in 2008, and is currently Mellon Professor of the Natural Sciences Emeritus at Columbia. Can I ask you please to join me in welcoming to the stage Professor Richards.
So, scientists, diplomats,
students, I thank you for inviting me. I'm fortunate to have had a lot of help in putting my career together and this lecture. Help over the last 40 years from colleagues at Columbia University and people in China and South Korea and Russia and other countries with whom I have written papers. But I am speaking only for myself, and most important, these other good people should not be blamed for any of the stupid things that I might possibly say. So let's remind ourselves of why we do this work. To improve methods of monitoring in support of various test bands. There have been several of them over the years, of which, of course, by far the most important is the Comprehensive Test Ban Treaty, which took on the order of 40 years to negotiate, and as you all know, is still not formally in effect. It's about discouraging the further development of nuclear weapons. And while this quote from a former director of Los Alamos is on the screen, let me tell you my plan for this lecture. First, I want to take you back 60 years to the 1950s, to a time when there was a strong political will by the premier of the Soviet Union, Nikita Khrushchev, and two presidents of the United States, Dwight Eisenhower and Jack Kennedy, with, at that time, some help from the United Kingdom under Prime Minister Harold Macmillan, who clearly, all of them, wanted to achieve a comprehensive test ban treaty 60 years ago, but they failed. A lot of the discussion of those years is well described by a book that I'm holding in my right hand, written by Glenn Seaborg, the Nobel Prize winner for his discovery of plutonium, who subsequently went on to become chair of the United States Atomic Energy Commission, and who was deeply knowledgeable about this era in the 1950s. And the foreword of this book is written by Averell Harriman, who, as special advisor to President Kennedy, went to Moscow and concluded a test ban, the Limited Test Ban Treaty of 1963, which banned tests in the atmosphere, in space, and oceans, but allowed them to continue underground, and it had no verification system. So how was that failure to monitor all environments apparent in that era 60 years ago? That's going to be the first part of my lecture. And in the second part, I'll try to convey how the principal technology for monitoring is practiced. How did today's capability develop over 60 years, since 1958? And then, in the third part, I'll give a brief report on some aspects of the very last nuclear test explosion, that of September 3, 2017, and its aftershocks in several senses, but I'll focus mostly on the scientific ones. So let's go back then 60 years, when Nikita Khrushchev in this year became premier of his country, the USSR, and Dwight Eisenhower had been in office in the United States as president for more than 5 years. It was a busy time. On this date, there had been on the order of 200 nuclear test explosions, almost all of them, 99%, in the atmosphere. Only one underground and fully contained underground, known as the Rainier test in September 1957, less than 2 kilotons. And at that first meeting of the Conference of Experts 60 years ago, a trilateral conference, was it a serious negotiation, or was it simply preparatory to the political discussion? There is argument today on that very question. But the Soviet delegation proposed a specific verification system. The United States replied with one conceptually about 5 times bigger. And the British, led by Sir William Penny, who had in his career developed in Aldermaston the leadership of the technical community developing nuclear weapons for that small country, suggested a specific system of 160 to 170 land-based control posts and a small array at each of them, and additionally to have some ships equipped to detect atmospheric and oceanic tests. This system, at that conference in 1958, was quite well received. And the final results of that conference are remembered today as the Geneva system, and it is, for example, described in one version of how those 170 or so control posts would be distributed with a few additional stations at sea. And here you see it, one conceptual distribution. That number, 170, is of some interest in comparison to where we are today with the international system, at least for seismic stations only, which conceptually is indeed composed of 50 primary stations and another 120 auxiliary. We'll come back to talk more about them. But how well, 60 years ago, was that system anticipated to work? So William Penny claimed at that time that it would detect and identify 90% of earthquakes equivalent to 5 kilotons or more, but there would be only a small percent, they thought at that time, detected at the smaller size down to a kiloton, and there would have to be some type of inspection system, it was understood in general, rather loosely, for those that could not clearly be identified by the understanding available at that time. So that was the initial concept, although very soon after 1958, other data came in with a much more pessimistic conclusion. And as I've said earlier, it was a busy time for nuclear tests. The United States had set off on the order of a bit less than 200 in that 1950s decade. This was a time of very big nuclear explosions occasionally in the atmosphere. 21 conducted in 1958 alone by the Soviet Union. The first underground test by the Soviet Union didn't happen until 1961. But what mattered in that era was a series of grossly inaccurate conclusions presented to policymakers as you see them in the first few lines of this graphic. Conceptually, the US Congress heard testimony that on the order of 100 to 500 seismic events would occur, mostly from natural earthquakes, but that would be indistinguishable, it was thought at that time, in their signals from serious nuclear testing at the 5 kiloton level and above. Well, today, here we are more than 50 years later, we'd say this number is zero. It's zero, but not at that time. So why was it so wrong? At a crucial time when there was a political will, albeit a technical community that was charging ahead with the responsibility it had been given in different countries at this time, notably in the US, the USSR, and the United Kingdom, to develop nuclear weapons. That technical community was doing its work, carrying out nuclear tests. The monitoring technology developed later and developed its own very substantial infrastructure over a period of decades, and that's what I'm trying to convey in this lecture. So those early conclusions were reached on the basis of minimal data at a time when seismology was feeble. Yes, there had been some understanding that close to a seismic source, go back. Close to a seismic source, going out about 1,000 kilometers, would be what are called regional waves. And if you wanted to detect very small seismic events, you needed to be fairly close. But going beyond 1,000 kilometers, we use the adjective teleseismic to describe the waves at that greater distance. Not quite so good as regional waves, but they became well understood. So these terms were followed. But in this era, seismology was a very sleepy science. Less than $1 million a year going into it in the United States alone. Very few people ever actually looked at a seismogram outside any institution that happened to record one. The data had the characteristic of what we call low dynamic range. That meant you could not record both weak signals and strong signals on the same system. And the only acknowledged method in that era for distinguishing between earthquakes and explosions was the idea, not yet properly investigated, that explosions always made signals that pushed outward or upward wherever seismic waves were recorded, whereas earthquakes sent out waves, indeed, which about half the time would have a first motion that was downward. Nothing else had really been firmly established. So that was the underlying failure. These regional waves that I've mentioned, a couple of them described here, I'll come back to that. But the outcome of that failure, resulting in specific characterization in the political world, as I've just described it, for example, in testimony to the US Congress, was, well, the limited test ban treaty which environmentally succeeded in shutting down nuclear test explosions in the atmosphere by the countries then carrying out such tests, and eventually atmospheric explosions did stop all around the world. The last was conducted in 1980. But nuclear testing moved underground to an extraordinary extent, on the order of one test a week for decades. Here are some of the numbers, and we could look at this for the next hour, but let me just make the following main points. You see, for each country on the list, especially the top two, large numbers of nuclear tests on the order of hundreds per decade in the 1950s and 60s and 70s and 80s, and a decline in the 1990s. In the era of primitive technology, when, for example, in seismology, signals were merely recorded in an analog method with a pen writing on paper or maybe photographically, the numbers are shown in red. Seismology became highly technical in the 1980s when more sophisticated instrumentation and digital recording became the global standard, and thereafter the numbers are shown in green on this graphic. And in the 20th century, well, these numbers declined. Only in the present century do we see on this last line the few tests in the Democratic Republic of Korea. But this is, at some level, an extraordinary change. For those of my generation, when I was a graduate student in the 1960s, seeing these strange signals about once a week, where there was a lot to do, and the nuclear weapons states in particular had an intense interest in studying the nuclear weapons development of other nuclear weapons states, and built up the monitoring technology to study that nuclear weapons development, not so much from the perspective of supporting an initiative in arms control, but to understand what potential adversaries might be doing. So, failure. Yes, an environmental success in shutting down atmospheric testing, but absolutely very little change in the development of nuclear weapons, because nuclear testing carried on, as I keep saying, on the order of once a week, without the general public recognition associated with mushroom clouds and direct concern over fallout. So, the outcomes. How to get monitoring to improve. And the President's Special Assistant for Science and Technology appointed a panel. Serious money began to be spent on the order, in the United States alone, on the order of $20 million a year. Money poured in from the perspective of the United States to study the nuclear weapons development of other countries around the world and to support the research and development effort. the worldwide standardized seismographic network was built in this era, and here is shown a graphic of 120 stations around the world built quickly, and in a textbook that I co-authored, written mostly in the 1970s. Today, I would have to say I'm a little embarrassed because my co-author and I wrote these words saying that the worldwide standardized seismographic network with its analog recording, not digital, was by far the finest general-purpose global system of seismographic stations ever operated. Incidentally, for those of you charged with the hard work of installing and operating a global network, this WWSSN was put in place in about 2 years. The secret to success, I'm told, by the people who did it, is fairly terse. No PhDs, no committees. Very competent people, engineers, just did it. Phone calls, station in Spain, do it. Call up the local geological survey people. Stations around the world, quickly installed, but some notable gaps. You see the largest country then and today in the world is not shown. Canada, another large country, in fact had a separate system. Today, and it took decades to put together, in that transition from, you remember I showed some red numbers, the nuclear explosions conducted when only analog recording was available, and then over a period beginning in the 1980s when modern instrumentation with digital recording came in, an IRIS consortium working with the US Geological Survey in the United States, with organizations in Europe, in Asia, and specific countries in Africa and all the other continents, installed and operates a system of open stations today, which absolutely has been used by thousands of scientists and has taught us so much about our planet, from regional signals, from teleseismic signals, to study seismic hazard, to study Earth structure. But let me go on then to describe in this period as seismology and other technologies began to develop, the understanding in monitoring the ongoing nuclear explosions around the world of the 60s through the 1990s was to try to break down the work into the different steps as you see them here, of detection, finding all the signals that come from any particular event, association, and so on, into if it was an explosion, how big was it, to do it for nuclear explosions then ongoing, for which there were no serious attempts to hide what was going on, or conceptually, if a country decided to try to hide a nuclear test explosion, how well could it evade a monitoring system? And who decided in this series of decades whether some capability was good enough or not to support a political objective, like a test ban treaty? Who decides? Well, I can tell you it was not the technical community. This, of course, is in the political realm. And that is as it should be. I think in our society we do not want a high priesthood of technocrats making our decisions. So I have no problem with the fact that the answer to that question on the last line is done with I hope, technical and scientific advice, but not the decision itself. That's a political decision. So, nuclear tests in the atmosphere, under the oceans, and then in 1962, buried at a depth of about 200 meters, but certainly not contained, as the Sudan explosion. It's kind of underground, but it left a big crater. The technology that developed to monitor potential adversaries can be, in a short lecture, described in these 6 main lines, which list the various technologies, and then the various columns that specify where they're effective for nuclear explosions in different environments. And working in the year 2000 to 2002, at the behest first of General John Shalikashvili, and then in a committee of the National Academy of Sciences of the United States, led by John Holdren, who became President Obama's science advisor, a group of us wrote a report from which I shall briefly quote. The energy released by a nuclear test explosion generates signals that are potentially detected by radionuclide sensors, by optical and other electromagnetic sensors, and by elastic wave sensors, that's seismic, infrasound, and hydroacoustics. The analysis of overall monitoring capability requires consideration of all available technologies, often in combination. What counts is the capability of the whole monitoring system. So, let us now then move on to describe the second part of my lecture, what is generally recognized both for this report and many others, and is the reason for why in this lecture I am emphasizing the seismology technology. And here is how it works. So this is the second part of my presentation. I want to give you a feeling of the underlying basis upon which seismologists do their work. And basically, if that blue frame is attached to the ground, and the ground shakes by going up and down, the green mass does not move so much, and it writes a trace on a piece of paper. That's the old-fashioned method of recording. So if you can show me that first movie, please. So earlier this month, an earthquake, not very large, in Alaska is shown here. And can I stop it? Yes, I think I can, and start it. So let's look at these waves. So I've stopped the movie. I'll start it again shortly. As we see it, we see, let's see, no, that's good. We see, after a few minutes, the waves that are strongest have expanded roughly in a circle at this moment. I've frozen it in time. And they're the strongest waves, as shown in this movie. Somewhat faster are the waves. We call them body waves, P waves and S waves. They've got out ahead. They're the fastest. And they haven't yet reached into the part of the world where I happen to live, New York. So let's restart it, I hope. Yes. And that first wave has arrived. Whoops, let me stop it. Well, so it's just gone past New York, and so it took about 8 minutes to get to New York. So the wave, after 10 minutes, is spread out. The strongest waves have not yet arrived, and It's not going to run it much more. Fine, thank you. Let's go back now to the PDF file. Thank you. Thank you. So, this is what a seismogram looks like in New York. What you see is that pen, and this is shown in an old-fashioned primitive way of displaying, that piece of paper wrapped around the drum, and as a pen writes its moving trace, this is the first arrival of those relatively weak waves after about 8 minutes, and then later the strongest waves arrive, and so it goes. So, how is this information used? And my point would be that it is used by thousands of scientists, and over the decades from that sleepy science of the 1950s, seismology, as by far the most quantitative of all the geophysical science, has taught us so much about our wonderful planet, details of the Earth's crustal structure, of the mantle, of the Earth's fluid iron core, and of the solid core at the center of our planet. And it's all done conceptually by this idea that if we have the seismic source, and off it goes, it sends a wave off, and after a few minutes, it's reached everywhere down into the Earth, but as it's shown here, has not yet reached the core, nor to the first of those green places where there might be a station. So now if you could show, please, for me, the second movie. It has the name Simon, I think, is the title. And my intent now is to show how waves, thank you, spread through the Earth's interior. And as they spread downwards, I'm going to freeze it now. So it's stopped after a few minutes. And throughout this presentation, I'm presenting something that really is complicated. But I want to make the point that that is good. It's complicated and it's good because if a country is trying to evade monitoring systems, there's such a complexity of waves that have to be addressed, which must be prevented from reaching sensors. In fact, the only, from the point of view of monitoring, it's so good that it's complicated because there are so many arrows in one's quiver as one tries to bring one method after another to bear in a global monitoring system. Frankly, the only problem that arises with this complicated system is somebody in my position who's trying to present all of this in less than an hour from start to finish. But you need have no sympathy for me. Let's make the point at this moment that the first station is the one very near, and it has acquired a permanent offset from that local seismic event. The waves have not yet, the red line is the seismogram so far, the point where I've frozen it, reached this station. Let's keep it going. And my word, what we have are these fastest waves. The P wave arrives here now. Hasn't yet reached the station. Keep on going. The other waves arriving, the strongest waves, are about to arrive at this station. Here they are, the strongest surface waves, and so on. Thank you very much. We will quit that movie and go back to the PDF file. And let's break down what we've just seen with an example. One of those modern stations in the open network available to the research community, has operated since the mid-1980s in China at a station called Urumqi, about 1,000 kilometers away from one of the Soviet Union's main test sites. And in 1989, a nuclear test at this test site wrote a seismogram at station WMQ. And here it is in a modern recording. And to give you a sense of what we're looking at, first of all, this is a useless record until we give it a time scale. So measuring time is really important in a seismogram. And this is time since the explosion went off. So the signal arrived at that station in China after about 120, 130 seconds or so, with the fastest wave that went through the Earth's interior, and so on. And it lasted, about 500 seconds before it came to an end. Let's keep on going. This first arriving wave, we call it a P wave, the primary wave, is a backwards and forth shaking, contrasted to the S wave of lateral motions. And latest arriving here are the surface waves. So the analogy for the P wave is to the longitudinal motion of the direction of travel is the direction of motion of the P wave. The secondary wave, traveling a bit more slowly, is a shaking motion perpendicular to the direction of travel. And then third, the surface waves arriving last. That's what slow means. And here you see them with their motions more confined to the Earth's surface. Those were the strongest waves that I showed in that brief movie of Alaska. So, now here's what we can do with modern analysis. We can take that red recording, and because it's digital, which didn't really happen on a massive scale until the 1980s, we can break it down. Now, if you close your eyes and hear my voice, you can probably tell that it's a man speaking, because I have a deeper set of frequencies. But someone else, a woman, a child, with a higher range of frequencies, one can tell, and this is my point, that the original seismogram contains the low frequencies and the middle range of frequencies and the very high frequencies. They're all in that record, and we can bring them all out. And in terms of how strong they are, it turns out that in that record, yes, there are the low frequencies, and this is a record of the velocity of how the ground is moving, only 19 nanometers a second at low frequencies, because explosions are very inefficient at generating those waves. And then at the other extreme, much stronger signals in the mid-range and at high frequencies. So this is how modern identification works. With your eyes closed, you can mostly tell the difference between somebody speaking, whether it's a child speaking, or in Shakespearean terms, it gets complicated, that the seventh age shifts, the sixth age shifts into the lean and slippered pantaloon, and then at the end of one's life, one's voice turns again to a kind of different way of speaking. But you can tell just with your eyes shut a lot about the mix of frequencies reaching your senses without having to use your eyes. And that's how seismograms are interpreted. Earthquakes and explosions put out a different mix of frequencies. So, on the left, you see an earthquake signal, and at high frequencies, the P waves and the S waves are in a very different ratio than is the case for an explosion, where the P waves are much stronger. So, let's move now to the third and last part of my presentation. I want to speak a little of what the modern capabilities developed over decades can achieve in application to the signals, as shown in this graphic, recorded at 134 stations of the International Monitoring System. We're looking at 41 primary seismic stations, 90 auxiliary stations, a couple of hydroacoustic stations, and one infrasound. This was an enormous explosion, and one of these stations, the one in Kazakhstan, at Akhtubinsk, showed that this last nuclear test explosion of September 3, 2017, in its green trace, is compared with the previous 5 traces of the earlier nuclear test explosions of North Korea, and it is about 10 times bigger. And for explosions all at the same depth, which isn't the case here, but that just gives you a guide that, roughly speaking, the size, the amplitude of these waves is a direct representation overall of the yield. This was an enormous explosion. And how well can we study it? Well, the best way to look at that, of intense interest to people in the Vienna International Center, as well as scientists around the world, when we apply modern methods today to the signals from the only nuclear explosions of the present century, we use necessarily a map of stations, and if you have good eyesight, you will see at this nuclear test center in North Korea, in red, where 6 explosions have been carried out, that it has signals recorded at one of the open stations in northeast China, and at a comparable distance to the station Ussurisk in Russia of the International Monitoring System, and at stations in South Korea, very close to the demilitarized zone. And I'm going to describe some of the findings that my colleagues have developed at Columbia University, noting that this last huge explosion and its aftershocks have been of intense interest to many different monitoring communities, and most interestingly, we now find extremely competent groups in China, in Singapore, in South Korea, and in other countries studying the aftershocks, very small explosions. So at MDJ, this station from which data is openly available to anyone in the world, here we see that the large nuclear test was followed about 8.5 minutes later by a signal, and then in subsequent months by seismic aftershocks. And the way these were discovered was to take one of them, it is actually this one, and to use a modern method called cross-correlation to search for weeks and months, and finding that in subsequent days, so the test explosion and a collapse of a cavity, but then a few weeks later, a pair of aftershocks, only magnitude 3 and a little, 2 more occurring again in pairs in October, a flurry in December, In February, there were even 2 more in April. They're not shown here. And the first issue would be, how confident can we be that they are indeed earthquakes, or might they be explosions? So we use a modern method that compares the P to S spectral ratios, which are large for explosions and small for earthquakes, and obtain the characterization, first of all in green, at that station, an open station in Manchuria, and in green, 10 of those aftershocks cluster with the earthquakes, but one of them, oh dear, clusters with our previous experience with explosions. Well, that's because we have pushed the detection capability down so low. We were talking about events now not much above magnitude 2, and at that distant station, almost 400 kilometers, by using cross-correlation as a detector, noise levels are high. The spectral ratio is not a very stable measurement, but fortunately, it's possible to acquire and work with data from the Ussurisk station, to work with data from the demilitarized zone on the South Korea side, and shown then finally in red is stations and their data interpreted for all of these aftershocks, but without the signal-to-noise problems of a very distant station, and with confidence these are all earthquakes. Let's look a little, again, carefully at the map, and shown, if you have good eyesight, from the test site are these lines coming down to stations in the Yellow Sea and many other stations in South Korea. And my colleague David Scharf has been able to use a modern method which has recently been applied to 5,000 earthquakes in China, locating them with unprecedented precision. In the last year or two, we can now do the work of precise relative location at the level of a few hundred meters, and in the present case, using what we call the LG wave, which is a kind of shear wave in the crust, a complicated wave with no obvious onset, but allowing precise measurements of its arrival time to within a few thousandths of a second, finding that primitive methods of locating all of those aftershocks in a map scatter over about plus or minus on the order of 10 kilometers, but when those aftershocks are located with a modern method, collapse on the same scale of map, almost to a point. And let's expand that point. So here are shown in our most recent work, submitted for publication earlier this month, is a set of the aftershocks. They trend over about 700 meters. They are located with a precision as characterized by these confidence ellipses that are just a few tens of meters. So this is the modern era. This is what we can do. This is not absolute location, it's relative location. And it's to me quite remarkable that these types of capabilities are now in place. So I want to conclude, first of all, with a quote from someone whom I greatly respect, with whom I disagree. His name is Freeman Dyson. In 1963, at that moment of failure, when only a limited test ban treaty was achieved, he gave testimony to the Congress, considering its advice and consent to ratification of the atmospheric test ban treaty. And he basically said, if you want to make political progress, keep scientists out of the room. He was quite stern about it. In my opinion, this man is one of the great theoretical physicists of his day. And in his words, in his testimony, when we reviewed 50 years after 1963, that would be in 2013, a group of us asked him how he felt about the interaction between scientists and diplomats. He was very stern. He basically said that the more sensitive the verification, the more frequent there will be false alarms. And indeed, some of those aftershocks I've described were originally, by some agencies, for a short period of time, announced as possibly these were explosions, additional explosions. But elaborate verification systems, said Freeman Dyson, allow opportunities for opponents to interject and prevent progress. Now, that's his opinion. But I see now that we've reached a certain stage, maybe not perfection, of course not perfection. This is a comprehensive treaty, but to do that work of forcing downwards in size the yield of any test explosion that might have military significance to a level where it really doesn't have military significance, that again has to be judged. But that is an achievement of a monitoring community, and in my opinion, it has been achieved. And so at the time when Freeman Dyson first expressed his opinion in 1963, seismology really was in dreadful shape. But over 60 years since the 1950s, and the other technologies too, we've achieved a tremendous result. Up until about 20 years ago, people could say, well, the verification system isn't good enough. But frankly, I don't hear that criticism anymore, and that is a terrific achievement, and I'm glad to have had the opportunity of describing it to you. Thank you very much. I don't know if we have time for questions or whatever your practice is.
We certainly do have a few minutes. If anyone wants to address some questions to Professor Richards, now is your opportunity.
Please.
Thank you for your presentation. I'm Aldila from Indonesia. I'm so interested with your presentation. In 1963, CTBT banned nuclear explosion in all environment, apart from underground. My question is, why does CTBT prefer to do underground nuclear explosion than others? And my second question is, does the underground nuclear explosion can trigger an earthquake? Thank you.
Okay. So, again, the second question I will answer first. In 1994, I helped to run a NATO conference in Moscow with the title, Earthquakes Induced by Underground Nuclear Explosions, and with experts from the Russian Federation and from the United States, from Europe, and from other countries. There was ample evidence that earthquakes are generated by nuclear explosions, but they are small. Examples were given of one test explosion. In fact, it was, yes, it was the one that I showed in July 1989 at the Semipalatinsk test site. The Russian scientists reported that it was followed by hundreds of aftershocks, but they were at the level of magnitude 2, 1, even smaller. None of any size comparable to the signals of the nuclear test. At the Nevada test site in the United States, occasionally there have been collapses underground of the cavity and occasional aftershocks, but much, much smaller. So it is true that claims have been made that nuclear explosions have triggered damaging earthquakes, but the intensive studies of that important question, to my satisfaction, have been answered, no, they do not do that. They do not do that. A lot of anxiety sometimes. I remember in the 1960s and 70s when a nuclear test was announced that it would indeed trigger an earthquake, but it has not happened. So, then I think your first question, do I understand it correctly, was this lack of ability to distinguish between the signals of an earthquake and explosion. They just simply make different seismograms. And it took us a period of several decades to understand how to distinguish between the two. They make a different mix of frequencies, and we now understand how to interpret those signals. I see your hand. Yes, please.
Thank you. Thank you so much for the presentation. It's very interesting. My name is Ana Avila. I'm from the Permanent Mission of Costa Rica. I wanted to ask you, because I see how the knowledge has increased in the last few decades and how scientists better understand the type of signals, the waves that are generated. Would it be physically possible for a country to design not one nuclear explosion, but a set of different explosions or other things that could generate the signals that would be sent by an earthquake? So would it be possible to mask a nuclear explosion along with other things in a way that it appears to be an earthquake?
Well, it's a serious question, and it has been reviewed in many different forums. And the short answer is you can't do that and get away with it for a nuclear test of the size that would have a direct contribution in programs of weapons development. I mean, I say that as a seismologist. I'm not a nuclear weapons designer. I'm just repeating conclusions that those who are more familiar with nuclear design aspects, as they reported first to the US National Academy of Sciences in this document, and then 10 years later, in 2012, in another review of this issue. For example, to carry out a small nuclear test in the vicinity of a large mining operation, which routinely will use literally thousands of tons of chemical explosive in the operation of the mine, making seismic signals from the chemical explosions. Could they be used to mask the signals from perhaps conceptually at least, a buried nuclear explosion in among all the chemical explosions that are ongoing all the time? And when you look at it in detail, that concentrated burst of energy from a nuclear test of size significant in the context of weapons design is really strong and stands out above the chemical blasts, which are commercially done for the purposes of fragmenting rock and have their own mix of seismic waves that is significantly different from the nuclear signal, which cannot be hidden. So, perfectly well, down to a very, very small size. There have been occasional nuclear tests that are formally nuclear tests with zero yield. Obviously, that is highly, but an example, a nuclear test to see if the device is in some sense exploded incorrectly so that it won't work as a nuclear explosion. In the United States, those types of one-point safety tests were carried out by exploding a nuclear device in a sense improperly, as might happen in an accident. And the test occurred and was not successful in the sense that it didn't have any nuclear yield. So it's formally a nuclear test, but it didn't have a nuclear signal. But again, this is a very specialized issue. This is not something that is associated with the weapons development program of a newly moving towards nuclear weapons capability state. This has happened in the past. I simply list it. There have been occasional nuclear tests to develop a level of safety in devices, though in decades in the past. But something that actually delivers a nuclear yield, if it does that, monitoring systems today, for example, in North Korea, just at the level of a few tons of energy release is detectable and, in my opinion, identifiable. Yes, perhaps the last question. Yeah, good.
Thank you. Hi, I'm Max Ho from Germany. I have I'd be interested in hearing a bit about the technological evolution in science and how that impacts the required number of monitoring stations. I mean, I get from the CTBTO brochure that the treaty has decided on 337 facilities. Is that number still necessary?
So the overall design of the IMS is laid out in some detail in the agreed text and its associated protocols and annexes in the mid-1990s and finalized in 1996. So that is when it was specified. And the friend of the chair, Peter Marshall of the United Kingdom, who presided over the process of deciding what technologies would be used and the overall capability intended in that era for them to achieve, wanted a system that would be able to monitor down to on the order of 1 kiloton tested in all environments. That was the working phrase at the time, and the system was indeed built. And in these types of technical report from which I have quoted, it's clear that the system operating today does far better than that. Okay? So the history is to achieve something at the 1 kiloton or something level. But in the regions where testing has occurred, a capability more than an order of magnitude better from that system alone. Now, the seismology technical methods are dual use technologies. And what has distinguished seismology is that the threat represented by earthquakes and the intellectual curiosity to learn about our planet is a separate driving force that has led hundreds of institutions to deploy today tens of thousands of high-quality stations. Not all of them openly accessible, but a significant fraction of them are. So more than 1,000 stations openly available in Japan, so on. So that is the driver, and to understand earthquake hazard, to do the work of documentation, means that an infrastructure of geological surveys and meteorological agencies has formed an infrastructure in practical terms far bigger than the nuclear weapons infrastructure of the nuclear weapons states, and that is not generally appreciated. It's outside the treaty context. Those people are deploying sensors for their own purposes that often turn out to be sensors in the right place and the right time, such as that station MDJ in China, to acquire data of intense interest to those studying particular nuclear explosions. So that is a force that will continue as long as we have a civilization. We need to understand earthquakes. We need to understand earth structure. So the connection to maintain professional standards between the work done in the international monitoring system and the International Data Center is good. For the work of tsunami monitoring, there's an agreement to work with data exchanges. So these are the ways in which standards will continue to improve, both in the work done in the CTBTO and intense interest just because of the way in our active planet, all these sources of seismic signal, of radionuclides, are of intense interest for purposes other than treaty monitoring. So we will continue to get better and better and better.
Thank you very much indeed, Professor Richards, and I hope we can all show our appreciation for his taking time to travel to be with us today. We're going to move on to the next session, which is on detecting the DPRK nuclear tests with Gerhard Graham, who is the Program and Project Coordinator in the International Data Center Division. Before we do that, now that you're mostly all here, can I just say thank you for helping me this morning figure out how to use our Symposium app to ask questions. So now we're going to use it before we move into the next session with a couple of DPRK relevant questions. So those of you who have downloaded the app, please ensure that it is refreshed and open and look out for 2 questions that are about to come your way. We're going to give you about 30 seconds to respond to each of them, and they will also appear on the screen in front of me. Question number 1. There's a very clear response to this one. How many nuclear tests has the DPRK conducted? Total votes 9, 12. Okay, we see some alternative views here. We'll wait a little longer to see how many responses we get. Okay, shall we move on to the next question? Yeah. Okay. Here we go. Approximately how many IMS stations contributed to the analysis of the September 2017? Can you put that back up again? Yeah, the September 2017 nuclear test by the DPRK. Yeah, here we see some different views. Maybe the first one was a little bit too clear-cut for everybody. No Googling is allowed, by the way, so I can trust your integrity on this, I think. We have over 50 votes here. I think that's enough for a quorum. There is a winner here. We see 40% or so going for option D, 125. So that is clearly ahead of the others, even if the margin is not quite as great as the response to the first question. But I can tell you that in both instances, the wisdom of the crowd is correct. So you have passed the first test that we have set you during the symposium. Congratulations. You're all on track to receive your certificate. With that, we're going to move into a little bit more detail on DPRK issues, and in particular on verifying the DPRK tests. So can I please ask Gerhard Graham to take to the stage. Thank you, Gerhard.
Thank you, Cormac, and good afternoon, everyone. I think I've had the benefit today that this morning you listened to radionuclide being explained. You've just had a very good insight into seismology. So I suspect about half of my presentation is done. But let's see. I also need to thank many of my colleagues in the IDC, also in the IMS. A lot of the material that you will see now were produced. Some of it, of course, mostly during the time between 2006 and last year, 2017, with the 6 nuclear tests that we recorded in North Korea. There's too many names to put up on this slide, but I'm merely using the insight and the hard work of many of my colleagues in the PTS. So this slide, I think, is now up for probably about the 3rd time. What else can I add to it? That yes, as Paul just said, it's complicated. Often one would hear that by merely comparing natural with an explosion type event, that it's very clear. This is, as we can see from last year, 3rd of September, strong P arrival, virtually nothing in terms of LG phases that arrive later at lower frequencies. It's often the case when we have events that's shallow. In the past, there were many projects, many research topics to use, for instance, shallow mining events to try and better distinguish between explosions and natural events. But I don't think that as we stand here, there's been a lot of work done on event screening, but it's certainly not a perfect science yet. And often one can get seismograms even from, for instance, in open pit mining where you have chemical explosions. Often these can look exactly like natural seismicity that is occurring. I want to stick my neck out a little bit, I guess, in quoting some ballpark figures as well here, that as we go from 2006 to 2017, one can see that the difference, it's a logarithmic scale in terms of the magnitudes, going from 4.1 in 2006 to 6.1 last year. And the traces here, the amplitude is it's a velocity measurement. And the difference is in ground motion about 1,000 times larger in terms of energy. It's 100 times, I also got it wrong now. In terms of ground motion, it's about 100 times larger, going from 4.1 to 6.1. And in terms of energy, it's about 1,000 times larger. As ballpark figures, again, it will not work out exactly like that if we look at it in more detail. And I may need my glasses for a second to read over there. So the role of the IDC. Often after nuclear tests in the DPRK, we've been asked questions. Is this a nuclear test? Was it a particular type of weapon that was used? IDC's role is very clear. It is to provide the information, the data, the products to our member states, who are then responsible for their national authorities to ultimately make the final decision. And I think next week, as you will experience the simulation, you will again play this game of having to face certain information. It's not always clear, but ultimately a decision must be made. Is this a nuclear test or not? We provide the data, the information, the products. We provide tools to our states' signatories. We provide the necessary training where possible, but ultimately it is up to the national authorities to ensure that the national data centers and their experts reach a level where they can take part in the communication and the decision-making around events of special interest. Right now we are in a provisional operation stage. We will be in provisional operation until such time as the treaty enters into force. And during that time, it is the opportunity to test the system, to ensure that what we're building and what we've built is in accordance with the specifications as provided in the treaty, in the operational manuals of the IMS and the IDC. And we see this as a verification stage. We refer to it as progressive commissioning, and we have just completed so-called phase 5A, which was the planning stage, and now some of the activities that we're involved in is the testing. We're no longer in just planning, but we're actually involved in the testing. Let me move to the next slide. So let's look a little bit in more detail. We've moved from 2006 to 2017. What has changed during that time? Well, in 2006, less than 60% of the network was completed of the IMS. Last year in September, we've reached over 85%. At the time of the first DPRK nuclear test, there were no noble gas systems in operation in the IDC. Last year in September, there were 25. We're continuously developing our software. I've already mentioned the fact that we were in phase 5A, which has since been completed, and probably we can also view the fact that as part of the testing of the verification regime, that these 6 nuclear tests, although not planned for, although at the time just before they happened, we were unaware, provided excellent scenarios and opportunity to test the verification regime. Again, on this slide, you'll see 4 what we can consider objectives during these tests. The first being, of course, we want to locate the position of the test very well. We want to ensure that we provide the correct information. And part of that is one of the products of the IDC, which is referred to as the standard screened event bulletin, which is essentially an event bulletin. It forms a subset of the reviewed event bulletin, which indicates which of the events that occurred or that are recorded in the REB we need to look at more closely. All the events that were clearly considered to be natural get screened out, and those that remain are events that either there's incomplete information or there's some of the parameters that we assess in the screening process that pointed that this may not be a a natural event. Now we should keep in mind here that the rule of thumb is, and the approach is, that we would rather leave many events in the so-called SSB not screened out for further analysis and to consider in more detail if necessary, than to have strict criteria and in the process screened out a nuclear event, a nuclear test. The criteria that we use for screening events typically is the surface wave magnitude ratio to the body wave magnitude. We look at the regional phases, the P2S ratios. We look at the depth phase. If it's a shallow event, you don't expect to see the depth phases. So all of these criteria that point to the event being an explosion are used in the screening, which is done completely automatic. It's not a manual process. It runs after the event has been analyzed, and it's been absorbed into the review event bulletin. In 2006, the first objective of locating the event was met within 2 hours. The so-called cell 1, and I think for those of you that were here yesterday afternoon in Ivan Kitov's presentation would have heard about the automatic pipeline. So this is the automatic process through which we generate 3 different types of automatic bulletins, the so-called standard event list 1, 2, and 3. The very first indication of a suspicious event is usually in the cell 1. And this was the style that occurred for all 6 of the nuclear tests that took place in the DPRK. Of course, in 2006, at the time, it's not on the slide, I think, but there were something like 14 stations that detected this event and were used to locate the explosion. So again, how does it differ from 2006 to 2017? The expectation for cell 1 was in 2006 2 hours. We are now down to 1 hour. And I'm not going to read through the entire slide, merely to say that as we started in 2006, also the expectations grew a bit tighter, and we have followed these expectations and managed for all 6 of the tests in reacting to those and delivering the data and the information, the products. All of these were done within what is currently envisaged to be the guidelines or the expectation after entry into force. Of course, while we, as an organization, is in provisional operation, we do not follow the strict guidelines, the strict expectations and requirements of the treaty. We do not work 7 days a week. We're not here 24 hours a day. We on usual business hours, 5 days a week. But during these tests, during special events, we of course do stretch our time in the office to provide the necessary response to our state signatories. As a very quick view of, again, the very first test, one can see the red is the, so let me rather start with what do we see here? The red and blue, the red is the information, the results from the automatic processing, cell 1. The blue is the human interaction that took place, the review after cell 3 was produced. And what we can see here is the reduction in terms of this so-called error ellipse. This is the area of uncertainty. It It reduced right down to, I think, approximately 880 square kilometers. And although I'm not going to get into any OSI discussion here, of course it is important because, as we know, within the OSI there is this limitation of the area that can be investigated being limited to 1,000 square kilometers. So this has always been seen that the so-called error ellipse should fall within this 1,000 square kilometer limitation. The two dots in the middle indicate the position of the event. This is a norm that is used in seismology. We always tend to envisage the location as a single dot on the map, but that's not entirely true. These ellipses that are shown here have a 90% confidence interval, which implies that the position of the event can be anywhere within, for instance, the blue error ellipse with the same confidence. What is also important, I've already mentioned that the PTS reaction was within the timelines expected by the treaty. So the REB, the Reviewed Event Bulletin, was released within 2 days after the event occurred. So on the 9th of October, the REB was released on the 11th of October. And maybe at this point I should just say a couple of sentences on typically what happens, because this has been the style. During from 2006 to 2017, the organization developed a certain procedure that we repeat, that we refine, and we've now had ample opportunity to test it. It's not to say that it's perfect. There's always room for improvement. But essentially from the time that we become aware of it, and with the time difference with North Korea, it's Vienna time, usually very early in the morning, anything from midnight, 12:30 to about 2, 3 in the morning. It usually comes in the form of a telephone call to our executive secretary or the director of the IDC that we get the first indication. Our own first indication is an hour after the event. This information is in cell 1, and this becomes immediately available as part of our products and data to the state signatories. So there's then a chain of events that immediately occur. It involves many telephone calls. It involves getting analysts into the office here at the Vienna International Center. It involves getting access to the data as quickly as possible so that some interim scanning can start taking place. Also, what is important is that for cell 1, we restricted to primary seismic stations because only primary seismic stations can be used to build the event. Now we can, and it's again an automatic process that will start calling on auxiliary stations to provide data. While this is happening, because right now the difference between cell 1 and cell 2 is 3 hours, that is enough time to get people into the staff into the office, analysts ready to start looking and reviewing the available information, so that usually by the time cell 2 is available, there's been a fair bit of interim review that's already taken place. Normally by the time that cell 3 is available, which is another 2 hours after cell 2, so 6 hours in total after the event, we've already had a good look. We've fixed, if there were any timing issues with some of the phase arrivals from the automatic process, we would have fixed that. And we have a very good insight in terms of location and magnitude. At this point, there's usually a call that goes out to have a technical briefing during which our state signatories are informed of this event, and it happens early morning, around about 10, 11 in the morning. From that point on, what the analysts are doing is to now work on that particular data day. So in this case, on the 9th of October, if at that stage, because in terms of the requirements or the relaxed requirements, I should say, of the provisional operation, we may be 4 or 5 days behind. We are allowed to be 10 days behind. We would then, out of sync, submit the 9th of October and whichever dates the other events took place on. So it is then important that we complete that particular day, which can only be done the day after, because with the event early morning, in terms of UTC time, it means that it's essentially up to midnight. So it's the next morning that we really then start completing the so-called data day of the day in which the nuclear test happened, because we cannot only release the information as an REB on the test. We have to release the REB with all the events that took place on that day. So in short, that is essentially the process that happens and has happened with every one of the 6 tests. Objective 2, I mentioned the SSB. In all 6 instances, these nuclear tests did not screen out. The automatic system recognized this as not of natural origin. It does not put up a flag to say it's nuclear. You cannot do that with the seismological information, but it can at least put the flag comes in terms of an index number. It's a value that is assigned in the SSEB to every event to indicate that this is not natural. At the same time, objective 3 was met, and again for all 6 events, this was the case where data and products became available, and not just for this event, but our usual day-to-day routines would have continued. And this was the case, if you can recall, in September 2016, we had the first of our experiments, as I've mentioned, as part of the progressive commissioning plan. And during that experiment, we actually had, on the 9th of September 2016, a nuclear test. The routine of the PTS continued. The IDC continued with its experiment, while at the same time we could also continue with the analysis of this particular test. Of course, at the time, as part of experiment 1, we were in fact working 7 days a week, although not 24 hours a day. I don't think I need, and you've seen this slide as well, and all I wanted to point out on this slide is the growth now in the IMS. And in addition, what we also see here is now not just seismic stations. This event was so large that we had one infrasound station that recorded the event, and 2 hydroacoustic stations. But in particular, in terms of the infra, we have to keep in mind that conditions must be right for the infrasound stations to record the blast. In fact, in 2013, which was the 3rd nuclear test, was also recorded at the time by 2 infrasound stations, purely because the wind direction at the time favored those 2 stations. At a quick glance, the six tests that took place from 2006 to 2017, we all know how the magnitudes increased over time. We can see how the number of stations, so these in brackets at the end is with the number of stations used in the location. We can see we started at 22, where we are today. The last test at 125, and also very important is the reduction in size of the error ellipse. We came from 880 square kilometers to last year a mere 109 square kilometers. Of course, the configuration of the stations that are being used, the number of stations will improve this error ellipse. In particular, if the number of stations and its distribution is such that it will start closing the azimuthal gap around the position of the event, but you will reach a point where you can add as many stations as you like. It will not necessarily improve the error ellipse. It may skew it a bit differently, it may change the shape a little bit, but ultimately the error ellipse, unless one now start improving timing of the phase arrivals, the knowledge on the velocity structure and so on, but you will reach a stage where it will not really be physically possible to decrease the size of that error ellipse. And this is merely the graphic representation of the previous table. I want to point out the fact that if you look at 2006 here, you'll see that it's to the west, more to the west. And the reason why I want to point that out is later on I'm going to show a slide where we've used relative location, and then we will see that this 2006 event actually moved to the east, and that is more in line also with results that were later on released internationally about the location of this particular event. As was mentioned, after the 2017 test, we've had a number of aftershocks. In fact, it started within eight and a half minutes after the main shock. We had the first aftershock around magnitude 4, 4.1. This information that you see here, it is purely based on IMS data. So again, the pattern that we see is probably a reflection of the stations that we have to our disposal. It's rather amazing to see how these events just sort of virtually converged with using different techniques. It's about 13 or 14 events there. There were, in fact, many more that we could identify through cross-correlation techniques, but very few of these events ever made it to the formal REB, because, again, as part of our event definition criteria, we need 3 primary seismic stations for an event to be taken up into the REB. In most of these cases, it's not the case. What we have is either a one-station solution with USARISC or KSRS, or a combination of the two with an auxiliary station. So we have this information in the late event bulletin, but unfortunately not more than that. Then another step that we took, this is, again, we developed this with, I think from the January 2016 test on. The treaty allows for further investigation, special studies that the organization may do, in particular to use additional information, or at the time when there is either late arriving data from the IMS network or changes in the data from the IMS network that can be used to improve our results. Again, this is part of the process of the commissioning of the entire verification system. And this is exactly what we've done, and we've for now concentrated in terms of the expert technical analysis on using relative location techniques to see how it could improve the location and if there were any changes in the magnitudes. And as a couple of quick slides, when we use all 6, let me rather say all 4, because we excluded 2006 and we excluded initially 2017. So if we use the 4 events in the middle as master events, so we flip between them as different master events, and we minimize the time residuals in terms of what is expected at the different stations, using the same stations always, versus what is theoretically expected versus what is practically seen. We minimize that time residual. We then get to the relative location, and this is where we will see the 2006 event now moving to the east. But they're all within a kilometer or 2 grouped together. The 2017, probably purely due to the massive size of this explosion, does not converge to a single point on the map. With very slight changes in the parameters, it moves around, and hence we ended up with an area in that green circle. So in that green circle somewhere is where the 2017 event will fall. And again, this is not unique. I believe there's other international agencies that went through the same and found the same as what we did here at the PTS. We used the same approach of the second event, the first so-called aftershock. And again, because it was so difficult to compare that to this massive explosion, it's not a single dot here. We now fixed DPRK 6 as a single dot in the middle, and now the aftershock becomes a little bit of a zone. And if we look at the coldest color, which is that sort of really dark blue in the middle, if you can see it here, that is the area that we think it would be in, because that's the area where there's the lowest time residual. And I thought to show this very quickly, because here we now see exactly those 6 traces again from the 6 different tests, and we can see this strong P arrival, very little later to follow in terms of surface waves. Well, let's go back. And here with the aftershocks, we can see in some instances very poorly developed P arrivals, but strong shear waves, LG waves that follow later on. And it ties in also with what was shown in the previous presentation by Paul, in this sort of eye, comparison by eye, that one can distinguish, but one must be very careful when you do that. So it's not just about the seismic network. What about the radionuclide network? Seismic data can pinpoint the event. It cannot tell us whether and we can use it to understand and to identify that it's not a natural event, but it cannot tell us what type of explosion this was. And this is where the radionuclide network is important, both the particulate and the noble gas systems. I think what I should just point out here is that, of course, if it's an atmospheric detonation, it will shower the particulate systems with radioactive isotopes, and it will be absolutely no problem to identify those, also as you've heard this morning with the radionuclide presentations. But if it's underground, it is less likely for those particles to be able to escape. It is more likely for a gas like xenon to slowly get to the surface and start propagating along the prevailing winds. And that's really what I want to very briefly show you in my last 10 minutes or so. It is that Yes, in 2006. Now you will remember and say, but there was no noble gas system working in 2006. Well, there was no noble gas system that was certified, providing data to operations in the IDC, but there were some noble gas systems that were being tested. And that's what we will use for 2006, and we did find a correlation. There was nothing in 2009 in terms of an observation that we could make. 2003 I will show you. 2006 mostly no observations that could confirm a nuclear detonation. Same in 2017, but at least I want to show you a couple of slides to see how close one can sometimes get, and then it's really, it's just not possible to say it is uniquely assigned to this particular source. So one thing we have to recall and remember though is that the fact that there is no observation does not mean that it's not a nuclear explosion. No observation just means I do not have the information, I do not know, I cannot say definitely. So, and I hope this animation is going, oh, it already started. So this was in 2006. This is some of the ATM that you also saw this morning. Now here you'll see the pattern grows. So that shows us as we continue for many days, and if we continue, eventually the whole of the northern hemisphere would be wrapped by starting at the site and doing a forward modeling to see where would the air at the time, with assuming continuous release, where would the air go following the wind and the wind directions. And one of the sites was Yellowknife. Let me run ahead with the result here. So Yellowknife was identified as a station that potentially could fall into this footprint of the cloud that was engulfing the northern hemisphere after the 2006 test. And what is very interesting here then is if we took the knowledge at the time of different or releases from different nuclear facilities, and you, as a sort of hypothetical analysis, then try and fit that to what would we expect at Yellowknife Station in terms of xenon release. This is xenon 133. This is the picture what we would expect. This is known releases from other nuclear facilities in the region. This is what was observed. And clearly, this strong peak that came about 15, 16 days after the detonation had no other explanation, although there is some indication here of a man-made, an other man-made release, not a nuclear test. We can already see that similar and slightly higher influences here only caused a little bump in the concentrations observed from the samples at this particular station. So from this, that was supposed to also, but let me just point out, so from that, we could then start at the station this time, at Yellowknife, and work our way back. So this is a backward model. It's a way of assessing now where potentially could the source come from. And the one other influence was here from Chalk River up here. The other in this area was DPRK, the test site. And hence, at the end, we could then say that in this instance, we could positively link the test, the release, several days later at one of the stations of the IMS that at the time was being tested. 2013, here we look at a slightly different scenario. This was Takasaki in Japan. I think also at the time not in operation but being tested. And here it was slightly different in that we saw two different types of isotopes. We saw xenon-133 and xenon-131. And I must maybe, just for clarification, when I say we, I talk for the team here, not for myself, because I was not here at the time. I've been around since 2016, so I saw the last 3 tests, not this. But what we can see here is that understanding the typical detections, the typical concentrations at the station, such as Takasaki, this is the pattern. And then suddenly, again, after the test, there were 3 consecutive samples that showed elevated levels of concentration, or elevated concentration levels of 133. Sorry, it came in. And this is 131. Now, separate, they're not enough to say it's definitely from a test site. But if we consider their ratios, and this is a technique that's been developed, that's being applied, is to take the ratio between xenon-131 and 133, and that can give you the age. It can be used to determine how long ago. We know it's a nuclear material, we know it's a nuclear source, but then the question is, how long ago was this release? And in this instance, we see these 2 readings which indicate a much fresher release. And if we worked it back, if I can go to the next slide, we will see somewhere it tells us 51 days ago plus minus 5 to 3 days. And that is, we often talk about the release from DPRK 2013 that reached a station 55 days later. And this was another positive confirmation. So one that was not so positive then at the end, or we could not give it the final tick of approval. This was the current setup in 2017, just the other day in September, of the stations that were being used in that region. I wonder if this will play. No. There it starts. So again, we assumed a very short release, in this instance from immediately after the test. Again, this forward model is to indicate the stations that we need to give special consideration at the time. Sorry. And what came from this was again a slightly different scenario. Here, Takasaki was involved again, but apart from at Takasaki, and now it's no longer 133 and 131, now it's just xenon-133, but there were 2 observations, one at Takasaki and one in Hawaii. RN 38 and RN 79 in Hawaii. So although there's also elevated concentrations here at Takasaki, we excluded that. We only looked at the 2nd of October, so approximately a month after the test, because these 2 samples corresponded with the same time frame at Hawaii. And if we then, I'm sorry, if we then apply the 2 different fields of regard, one starting at Takasaki, one starting at Hawaii, we overlay them we get this picture here. So this picture is an overlap created through a backward modeling from the stations in terms of the field of regard to get the possible source region. But in this instance, although part of it, this is the test site, although part of the source region or one of the source regions was in the vicinity of the test site, we could not uniquely say that's the only area that it could come from. There were other possible source regions as well. Very briefly on the this Russian station 58, Usurisk. Here again we had a comparison of xenon 131 and 133, and let me go here immediately. There were two episodes, the one on the 24th of September, the other on the 19th of October, in the getting the ratios between the two isotopes. This is within a well-known region, I think I could say, so there was nothing unique about that ratio. This one fell slightly outside of what is usually expected, but again, not uniquely and strongly so that we could say that this is definitely from the release at DPRK. And at that point, I think I'm going to stop, and if you have any questions, please.
Thank you very much. My name is Yumei. On your slide, page number 23, you said the explosion of 2016, there's no radionuclide detected, right? In this case, I would like to ask if there will be some release of the noble, radioactive noble gas, only if there are some cracks. Yes, and in this, in 2016 tests, there's no it's not this slide. Maybe I'm not. Okay, is it? You said 2016 nuclear test. There's no detection of noble gas. Is it correct or? Yes. If it's correct, I would like to ask. There will be some release of radioactive noble gas after a test only if there are some kind of cracks. And if there's no detection of the radionuclide or noble gases, does that mean that the tunnel is not deep enough, or it's due to the explosion or the cracks formed after the explosion, or the cracks were already, I mean, before the explosion, there were some cracks inside of the rocks. And what is the reason actually for the non-detection of the radionuclide after a nuclear test?
Okay. So let me just say, yes, it's not as though there were no detection of radioxenon. In both instances in January 2016 and also in the September 2016, there were detections of radioxenon, but we could not uniquely assign those releases that we, or the detections that we made to a release from the test site. Not as in the cases that I've just presented. And indeed, one would need, there's many conditions at a test site that will determine whether radioxenon will be released or not. the type of geology. All types of rock has got a particular permeability, and the more porous, the better the chance of the gas being released. Cracks, as you say, a blast that size in particular can open up cracks that the gas can follow. It may take some time, but once it gets to the surface, it may take a long time to get to the surface. It may take, and in that time, of course, the source, although still very hot, will gradually release less and less of the gas. But once it gets to the surface, there are now other conditions that may play a role. The wind direction may not favor some of the stations in the immediate vicinity. Rain may play and may influence the concentrations that do get carried away further from the site. So there's unfortunately many conditions that one must take into consideration, and at the end, although we measure xenon at sometimes at many stations afterwards, they cannot be linked to the release. We have to, at the end, find in our possible source zone that it links up with the release or the area of the test where the test was conducted.
Do you believe it is possible to artificially create such conditions and facilities to actually deceive the IMS?
I think it will be very hard. It is probably a topic that, well, it certainly at some point, I guess, it was a very active topic, how to hide nuclear detonations. I think in this time and era with modern equipment, I would not say it is 100% not possible, but I think it is very unlikely that that it can be hidden. We know what the IMS is a global system. We know what it's designed for, and if we operate within those conditions, which as a minimum provides for 1 kiloton, I think it will be very difficult to hide it.
The 2006 DPRK 6 nuclear test generated many aftershocks from 2006 until 2018. But when we see them, we see that they are separated in time. But for that, I want to know if before the test was being conducted, if the region was not seismically active, because you see that not only they are very separated in time, but they are not matching also with the radionuclide observations.
Let me just understand exactly. So you refer to 2006.
Yeah.
So 2006 was the first test. As I said, it was before my time here, but I'm not aware of any aftershocks. It's not to say at any point if one disturbs the natural stress field, you would expect that there is some sort of a reaction So it's not to say that there could not have been a few aftershocks for each of these blasts. But again, the IMS is a global system. It is not designed to go pinpoint magnitude 1.5 or 2 in particular regions. Hence, I made the point that even the larger aftershocks after the September 2017 event, is only a few of those that for now has only made it into our late event bulletin. So we have limited data on those. Someone once said to me, well, if you put a seismometer or a series of seismometers anywhere on the earth, you will start recording earthquakes. I don't know, because I have no insight into the background seismicity of the test site. It would be interesting if one had a local network before and after. It's entirely possible that there's some level of natural seismicity, but I still believe it is the same as when you build a big reservoir or when you're mining at 4 kilometers deep, that the disturbance in the local stress field can certainly enhance the level of seismicity. But that's still, in a way, it's still natural, although I think when you set off a very large explosion like last year, then certainly one has to think that the faults and whatever geological structures in the close vicinity will react and will have to settle again, and it will take some time. So these, what we now call aftershocks, may continue for some time, but we also know they will get smaller and smaller up to a point where we just wouldn't know that they're there probably.
Okay, my question is, what is the main, or what are the main difference between, let's say, an earthquake of 4.1 magnitude and a nuclear explosion of 4.1 magnitude? So, what is the difference between those two signals?
The signals are, from a puristic point of view, an explosion is spherical. So it is, one must imagine this as its ball shape, and it propagates rapidly away in a symmetric form from the source, and it should give rise to compression all around it. So one would expect to see very sharp and large amplitude P-wave arrivals in all the stations around it. An earthquake is far more complicated. An earthquake, there's many different sources, but we always refer, the easiest one is a strike slip, where part of as there's movement, let's say along a fault, part of that fault is pushing, part of that fault is pulling. And that creates a more complicated waveform that will usually give rise to a more emergent, smaller amplitude P-wave arrival, but it will create a more complicated train of different phases that will arrive later on. So, and this is now excluding the effect of the earth, the crust that the waves propagate through. But that's essentially, theoretically, should be the big difference, is that on the one hand, it's a simplistic source that is mostly just a compression versus a complicated source that has compression and dilatation in it. But as I said, in reality, because of interaction with interfaces in the rock mass and all sorts of reverberations and reflections that we get along the ray path, it's not what we always see.
I think we're going to have to slowly come to an end. Sorry about that. As I've said a few times before, if you have any more specific questions, we can direct them to Gerhard, or you can do so yourself, or other people indeed who might be able to answer those questions. So we're going to move on to the next session, which is on the civil and scientific applications of the CTBT and its verification system, and it's going to come in two parts. We're going to hear from Patrick Grenard, who is the Director of Administration at the CTBTO, and not only that, but he's somebody who has many years of experience with the verification regime, and who in more recent times as well has been working to connect the value of CTBT science with global initiatives for the common good, including the Sustainable Development Goals, initiatives in disaster risk reduction, and much more besides. So we will start the session with a presentation and explanation from Patrick on that, and then Elena Tomuta will continue with more specific information about the various applications and spin-offs, as we sometimes call them, of CTBT technologies outside the mandated area of detection and monitoring of nuclear test explosions. Thank you.
Thank you, Cormac. Good afternoon, everybody. So before we get to Elena's presentation, I really would like to give you a little bit of background and some contextual elements to our discussion this afternoon. So I guess now that we are on the third day of the symposium, so you all know that the IMS consists of facilities in over 90 countries to verify compliance with the treaty, with stations and laboratories using seismic, radionuclide, hydroacoustic, and infrasound technologies to monitor and detect any sign of nuclear explosions. Our international data center in Vienna provides state signatories with IMS data and data products that can catch any country going against the no testing norm. So this has been the case for each of the 6 tests conducted by North Korea between 2006 and 2017, as just illustrated by Gerhard Graham in the previous session. But in the process of scanning for nuclear explosions, IMS stations pick up signals from an abundance of anthropogenic and natural events. This data is unique and is a treasure trove of knowledge with a broad range of civil and scientific applications. This includes earthquake observation, tsunami warning, and the broader area of disaster risk reduction and climate change monitoring and research. By contributing to addressing key societal issues, we expand the benefit and value that the treaty provides to the international community. Early on, CTBT state signatories clearly recognize that the unique CTBT verification system offers a host of opportunities for applications in everyday life and scientific research. The process to evaluate how best to tap into this vast potential was initiated in 2002 in London. It's often known as the London process. It was initiated by the late Peter Marshall, a seismology expert from the United Kingdom and a veteran of the CTBT negotiation, who chaired the first meeting. But it's important now to see how this process fits into a more global perspective and to underline the importance of an integrated, multidimensional approach to contribute to what countries have defined as institutional priorities for the United Nations as a whole. On September 25, 2015, countries adopted a set of goals to end poverty, protect the planet, and ensure prosperity for all as part of the 2030 Agenda for Sustainable Development adopted by the United Nations General Assembly. So there are 17 Sustainable Development Goals that were approved by the Assembly. And each goal, the SDG, each Sustainable Development Goal, has specific targets to be achieved by 2030. As you can see, some of the SDGs resonate well with our core mission, such as peace, justice, and strong institutions. And our actions align pretty well with the Sustainable Development Goals. For instance, eliminating nuclear tests, reduce negative impact on the environment, agriculture, oceans, climate, health, and promote redirection of wealth to areas of well-being. The IMS provides near real-time global monitoring of the planet with applications for health and the environment. Our capacity building and education programs support global empowerment, equality, and economic development. The IMS data contribute to seismic hazards analysis, tsunami warning, aviation flight safety, all aspects of resilient civil infrastructure. The global disaster risk reduction objectives have been further defined in the Sendai framework, that is a 15-year voluntary, non-binding agreement which recognizes that the state has the primary role to reduce disaster risk, but that responsibility should be shared with other stakeholders, including local government, the private sector, and international organizations. It was adopted by UN member states on 18 March 2015 at the third UN World Conference on Disaster Risk Reduction in Sendai City in Japan. The framework has 4 priorities for action: understanding disaster risk, strengthening disaster risk governance to manage disaster risk, investing in disaster risk reduction for resilience, and the 4th priority, enhancing disaster preparedness for effective response and build back better. But the framework outlines 7 global targets. First, to substantially reduce global disaster mortality, numbers of affected people, economic loss in relation to global GDP, disaster damage to critical infrastructure and disruption of basic services, but also to substantially increase the number of countries with national and local disaster risk reduction strategies by 2020, international cooperation to developing countries, and access to multi-hazard early warning systems and disaster risk information and assessments. CTBTO actively participates in the Sendai framework for disaster risk reduction and is represented in the UN Senior Leadership Group for disaster risk reduction. Our contribution is of particular relevance in the last 2 targets: international cooperation to developing countries and access to multi-hazard early warning systems and disaster risk information and assessment. For instance, in the event of a nuclear accident or other radiological emergency, we provide timely and accurate response through the Commission's membership of the Interagency Committee on Radiological and Nuclear Emergencies, IACRANE. It's very difficult to pronounce. In June 2016, the organization and the IAEA signed a practical arrangement on nuclear emergencies to cement our cooperation based on IACRANE and the Joint Radiation Emergency Management Plan of the international organizations. By establishing partnerships with relevant multilateral entities, we achieve synergies and leverage resources. Those partnerships, in return, allow us to strengthen the networks of support for the treaty and its verification regime. So it's a two-way street cooperation. In particular, cooperative links with academic and research institutions inspire new research on nuclear test monitoring technologies and the civil, scientific, and industrial applications of monitoring data. It also contributes to maintaining the scientific relevance of the organization and to the sustainability not only of our systems, but also of our human capital. That is really key for this organization. We promote and facilitate the use of our data for disaster warning and scientific studies, including through a virtual data exploitation center. You will hear more about it in the last session of today. And we make this virtual data exploitation center available to scientists and institutions, but also we promote the use of data for civil and scientific application at our biennial CTBT Science and Technology Conference. It's called the SNT series, and which is the main scientific forum to discuss CTBT verification and other uses of IMS data. The next SNT conference will take place in Vienna in June next year, and I hope that many of you will be able to participate and to continue providing innovative ideas through the use of our data. So I just hope that this general introduction has provided you with some elements of the global context, and while we remain focused on the primary mission of the organization, that is treaty verification, I just hope that it highlighted how important it is for us to make sure that we maximize the value and return on investment to the international community, that we leverage existing resources, that we look for cooperation and synergies, and after all, that we avoid operating in silos. Thank you very much.
So good afternoon, everyone. After this high-level introduction by Patrick to the way that the CTBTO supports the Sustainable Development Goals, I'd like to go into a bit more detail on some of the civil and scientific applications of our data and products. Several of them were already mentioned just very briefly by Patrick in his statement. So you've learned in the course of yesterday and tomorrow morning everything about the International Monitoring System Network, and also about the way we acquire and process data from this network and produce analysis results that we make available to our member states. Of course, the main consumers and beneficiaries of this data are authorized users in state signatories that use our data and products for test ban treaty monitoring purposes. But aside from this, we also have civil applications that were developed and make use of the data of the IMS and the products built from it. And I'll be briefly talking about tsunami warning, radiological and nuclear emergencies. And we also have a mechanism to provide research institutes around the world with access to our data and products on one hand, as well as to access to a test environment that they can use to develop and test new methods, either for the purpose of treaty monitoring or for civil and scientific applications of interest to them. And this is the Virtual Data Exploitation Center that Patrick has mentioned. It is both an IT platform and a legal framework that allows us to make available our data and products and to engage with researchers around the world to develop applications based on these data and products. So looking at our primary partners in member states, these are the national data centers, or NDCs as abbreviated on this slide. And we have at the moment 144 registered NDCs, of which more than half are engaged, have, in addition to the treaty verification mission, also a mission in relation to disaster mitigation. They are seismological observatories or radiation protection agencies or institutes engaged in disaster or emergency response. So the NDCs are our primary counterparts with which we work together to further treaty verification. They are supposed to be able to reproduce the results of our analysis, and they are also the first point of contact and centers of expertise for treaty verification for their country governments. In addition to NDCs, there are also other designated establishments that do not necessarily play a role in treaty verification, but have access to data and products. And of these, you can see that about a third also have a disaster mitigation mission. So for this reason, there is this area of disaster mitigation, which is one of the, which is also one of the SDGs that was mentioned before, is quite a focus for the CTBTO community in terms of developing civil and scientific applications. And of course, the most immediate use of our data is for seismology. We have several seismological observatories among the NDCs and register establishment, and what happens there is that these observatories often have a role in seismic hazard monitoring and alert in their countries, and they combine data of the IMS with data from their regional and local networks, and also other open source networks, as Professor Richards mentioned earlier today, to fulfill this monitoring mission. At the science and technology conferences, we also see a fair number of studies in the area of earthquake hazard assessment. So this is perhaps the most widespread application outside treaty monitoring purposes of our data. Another one that is a combination of seismology and hydroacoustic monitoring is tsunami warning. There was a greatly increased interest in tsunami warning, obviously, after the Indian Ocean earthquake and tsunami of 2004. And following that event, the policy-making organs of the CTBTO were asked to review the possibility of making available data from IMS stations to tsunami warning centers to support them in their work. The entity that somehow coordinated these efforts was the Intergovernmental Oceanographic Commission, IOC of UNESCO, and following a couple of years of review and negotiations, the policy-making organs approved forwarding of data from stations of the IMS to designated tsunami warning centers. So there are currently 98 stations that are used for tsunami warning, and this data is, and we have agreements, formal agreements, with 15 of these tsunami warning centers in 14 states. So the general idea here is that there's seismic data and seismic events that are used as a trigger to determine that possibly a tsunamigenic event occurred. And then in addition to that, there's more in-depth monitoring measures that are looking at rising sea levels using buoys that are installed offshore and onshore tide gauges. So our data plays a role in this initial determination of a potentially tsunamogenic event. And you can see on this slide the amount of data that we make available to each of these tsunami warning centers. These numbers grew from 2009, when we first started this forwarding, until 2014, and then we reached a plateau more or less in 2015 to 17. You can also see at the top of these bar charts, of the bars in this chart, the number of centers that actively receive data in each particular year. And we now have 12 of these 15 centers that actually receive data. The second area or the third actually area of civil applications I would like to mention is related to the infrasound technology. Obviously, there are many possible applications of infrasound, such as detecting and locating chemical explosions near the Earth's surface, detecting and locating meteorite impacts, tracking storms, and one I will speak about in a bit more detail, volcano ash plume warning for air flight. So as far as volcano eruptions are concerned, major eruptions can disrupt civil aviation because they may release ash clouds into the atmosphere that constitute a hazard for aviation. And this is a concern for the International Civil Aviation Organization, ICAO. And ICAO essentially has a plan to put in place mitigation measures to manage air traffic in the case where such events occur. The supporting program of ICAO is the International Airways Volcano Watch, and this International Airways Volcano Watch establishes 9 volcanic ash advisory centers that advise ICAO on possible volcanic eruptions that might cause ash plumes to be released into the atmosphere. So the map shows these 9 volcanic ash advisory centers and their area of responsibility. So what is happening here is that the volcanic ash advisory centers coordinate and disseminate information on these clouds, and they use a multitude of monitoring techniques. Some of them are seismic sensors that are installed in some cases in the vicinity of active volcanoes, but there is also remote sensing, and there are also observations by visual observations or reports of pilots that pass with their aircraft close to the volcanic eruption. And the idea is that infrasound technology may supplement these other techniques for monitoring volcanic activity, especially in areas that are poorly instrumented, so remote areas where we don't have sensors that can determine that a volcanic eruption occurred. And this is an example of the synergy between CTBTO and a project, an EU project called ARISE, and ARISE stands for Atmospheric Dynamic Research Infrastructure in Europe. It brings together several research institutes with the aim, on one hand, to provide observations and models that improve weather forecasting on monthly and seasonal timescales, but also to provide multidisciplinary data and tools to analyze atmospheric extreme events and climate change. And one of the declared aims of ARISE is to propose remote volcano monitoring techniques and provide notifications to civil aviation. So we have on one hand the CTBTO operational infrastructure, which is built for treaty verification purposes, with the IMS network that is being maintained, and with the bulletin of infrasound events that we generate operationally on a daily basis. and on the other hand, these additional modeling research capabilities and additional instrumentation provided by ARISE. And the result of this was the development of the volcanic parameter system by the ARISE members that aims to combine IDC attributes of infrasound stations detection with other parameters coming from the ARISE databases. So after an initial development and testing in an environment similar to the one we run here at the CTBTO at the International Data Center, this prototype is now installed on the Virtual Data Exploitation Center and is being evaluated by the VAAC Toulouse. So if this reveals that this is a promising application, civil application of our data, then the next step will be to ask the policy-making organs of the CTBTO to review this application and to potentially make IMS data and products available to the volcanic ash advisory centers such that the system can be run in operations. So this is an example of an application that is at a lower technology readiness level than the, for instance, tsunami warning that I mentioned before. And with this, I'd like to go to the area of radionuclides. Here, our involvement in radiological protection and our capabilities were demonstrated by the Fukushima accident on the 11th of March 2011. And I'm not sure how well you can see this animation at the center of the slide, but essentially this shows observations at the IMS stations between the 13th of March and the 29th of May 2011. And you may remember from the presentation on radionuclide processing earlier today, I think, that we assign to each of the samples that we acquire from these radionuclide stations a category that essentially says something about the fission products that were detected in that sample. So this shows the evolution in this time frame of detections at IMS stations. And of course, this is a very interesting and important information to have as part of a response to such an event. So what happened then after the Fukushima accident was that on the 15th of March 2011, we briefed member states and drew their attention to the capabilities we have that could assist with emergency response for this event. And then after the 17th of March, we made available radionuclide observations only related to this particular event to the International Atomic Energy Agency and the World Meteorological Organization. On the left-hand side of this slide, you can see an example of an ATM simulation. You've also learned about this earlier today, that shows how the air masses originating in Fukushima moved across the globe in the days following the March 11 disaster. So after this event, we became involved in the Interagency Committee on Radiological and Nuclear Emergencies, and Patrico mentioned this in his statement already. This happened already in April 2011, and then in March 2012, we became a member of this committee. So this committee basically coordinates, brings together UN or international organizations involved in emergency response for radiological emergencies or nuclear emergencies, and it is coordinated, the secretariat is provided by the IAEA. Among others, it produces standard operating procedures and has guidelines on sharing of information and public communication in the case of such an emergency. And its main one of its main documents is the Joint Radiation Emergency Management Plan, or the J Plan. And this J Plan now also describes the role that the CTBT plays in preparedness and response. So in general, in terms of preparedness, we continuously gather real-time particulate and noble gas data. We do this anyway in the course of, for treaty verification purposes. And then during an emergency phase, in the critical response task, we provide this data to the IAEA to support the response. After this critical phase, we provide results on radionuclide air concentrations based on our analysis. And there's also advice on expertise in global monitoring in radionuclide air concentrations and advice on atmospheric transport and dispersion predictions. Right, and I wanted on one of my last slides to highlight a couple of other civil applications that various research groups work on, and one common theme for all of them is that all of these images and information come from presentations at the Science and Technology series of conferences, which Patrick also mentioned before. So this is one of the major venues where you can learn about how the research community, scientific groups around the world use IMS data and IDC products. So you can see, remaining within the area of infrasound, there are studies on atmospheric dynamics using the beryllium-7 tracer. So this is a type of radionuclide that is detected by by our radionuclide stations, and the data series of activity concentrations of this tracer at various stations around the world gives indication of atmospheric dynamics. So one of the results in the course of this study that was presented at the last Science and Technology conference was a correlation between levels of this tracer at 2 IMS stations and the onset of the Indian monsoon. So this could point to a possible future application of this beryllium-7 concentration. A topic that has captivated the research groups for a relatively long time is tracking icebergs and detecting calving of icebergs using hydroacoustic measurements at the IMS hydroacoustic stations. So already in one of the first S&T conferences in 2009, there was a presentation that tracked a particular iceberg using these hydroacoustic source locations and compare this with results obtained from a NASA Earth observation satellite. And finally, I mentioned already the RISE project, which has to do on a theoretical level with infrasound analysis of vertical wind and temperature structure, and possible applications that might result have to do with tracking severe storms, possibly later on alerting about severe storms or severe weather phenomena. So to conclude, as you already heard in the course of these last 2 days, we operate a unique network of highly sensitive sensors of waveform signals and atmospheric radioactivity, whose main purpose is nuclear explosion monitoring, but there are several civil applications that were developed on the basis of this data with the intention to mitigate the impact of natural and other catastrophes, and others are in the process of being developed using this mechanism of the virtual data exploitation center through which we engage with the scientific community. And something that perhaps wasn't mentioned so far is that we also have a capacity building and training program And this capacity building and training program assists national data centers primarily and register establishment in using the IMS data and products. So primarily for treaty verification purposes, of course, but also for other areas of interest to them. Thank you.
Okay, please.
Thank you very much. My name is Stephen Herzog from the United States. And I think that the civil and scientific applications of IMS data and IDC data products are absolutely critical, in large part not just because of what they can do, but because of the non-universal interest in nuclear explosion monitoring in the international community. There are, of course, a lot of states that may just genuinely think that nuclear explosion monitoring in the CTBT is perhaps irrelevant for them, or is for states that have more resources or larger states. But it's one thing to kind of talk about the civil and scientific applications of the data here and at the Science and Technology Conference Series. But of course, you know, these data can have real implications, I think, for getting remaining countries to sign on to the CTBT, to ratify the treaty, possibly to install and get certified the remaining IMS stations, which are not part of the network, and maybe even to create NDCs for the countries that don't have them thus far. So I know that the mission of the CTBTO and the PTS is to monitor the globe for the absence of nuclear explosions, but my question is besides kind of mentioning the civil and scientific applications at conferences and workshops and doing capacity building work, how much of a role is this playing in high-level PTS diplomatic outreach to countries related to the IMS and signature and ratifications? Thank you very much.
Let's take a round of questions and then we'll address them. Let's take one or two more. Okay.
Thank you. I'm Max Ho from Germany. Could you say a few words about how long it actually takes, or within what time frame the IMS data is transmitted to some of the other, for instance, to the tsunami warning centers? Thank you.
Okay.
My name is Estelita from Indonesia. That's a really great presentation before. And I'm asking about the civil and scientific application of the CTBTO monitoring. By the presentation previous, I can learn that the IMS is working to prevent the to prevent and then to warn people about the potentially damaging earthquakes and then the other disaster and natural disaster. And then, but what the role of the IMS and IDC and or NDC to fix what has been done by the nuclear weapon test before, like the radionuclide gases in the environment and the other damage that has been done before? Thank you.
Okay, maybe I'll start. So we'll start with Stephen's question first. Indeed, you're right. When we meet with potential signatory states and the benefit of the treaty is one of the first questions that we get, beside the participation in global security infrastructure, improving security of the world, nuclear non-proliferation and disarmament. It's very clear that when we start talking about civil and scientific application, this is gaining suddenly a lot of interest. And we do have regional conferences or national seminars and many opportunities, and besides the Science and Technology Conference or Science Diplomacy Conferences, where we meet local stakeholders or authorities, and when we have the opportunity really to get to the bottom of the benefits that a state can get by joining the CTBT. and can start by installation of an IMS station, getting acquainted with the technology, getting training on the monitoring technology, then supporting the establishment of a national data center. So then it's a possibility to get access to all the data and products. Then it's capacity building. The capacity building program, developing capacity in all the verification technologies. And as Elena mentioned, we have developed a software suite that we distribute to national data center that enable them to integrate their own national data or regional data with CTBT data so that they can use those data not only to support 3D monitoring, but also to support civil scientific applications. And this is really the best sustainment model that we can promote when we get to a country, we get to meet with academia, civil society, national authorities, and be it people and dealing with health issues, meteorological issues, hydrology, and so on. When we get all those stakeholders around the table to discuss the potential benefit, for us, this is the best way to get the systems we install in those countries sustained for a long time, to get people interested in the treaty, because then they join our capacity building programs, some of them, and get trained, apply for positions, and work at CTBTO. And this is why I mentioned in my introduction this notion of sustaining the human capital. So it's not only about science and instrumentation, making sure that we have this constant flow of talented people, motivated people to join the organization is really critical. So it goes really beyond mentioning it at the science and technology conferences. Indeed, we see it happening for real when we deal with actors in the different signatory countries or countries and potentially interested to sign and do further engagement with CTBTO. And, you may want to take the second one.
Yes, so the second question was about the time frame in which tsunami warning centers receive data. So this is a very short time in the order of very few minutes. I could not tell you now an exact average number, but as you heard this morning, as far as our data analysis is concerned, we process data on a schedule that is based on 1 hour, 4 hours, and 6 hours after real time that we produce standard event lists. Now, this, of course, is much too late for tsunami warning, which is one of the reasons why the decision was made to not provide analysis products, but to provide the data itself, the raw data itself, to tsunami warning centers. And we have a continuous data protocol that we use in the communication with the stations, and all of the stations that we provide as part of this tsunami warning effort arrive immediately as soon as they are recorded at the station, are transmitted via the global communication infrastructure to the headquarters in Vienna, and from there they are forwarded to the tsunami warning center. So this is a very, very short time frame that elapses until these centers can get the data. Third?
I don't know if on the third one you want to...
Yeah, I can. So the third question was about the role of the IMS and the IDC, and how does seismic hazard monitoring play into this, or what is the relation with the main role of the IMS and the IDC. And of course, the role of the IMS and the IDC is nuclear test ban monitoring. That is clear, and that is our mandate. All of the civil applications that I mentioned in my presentation are developed and are run by other parties around the world, national data centers, research institutes, and of course we do our best to facilitate the use of our data for these purposes. and there are arrangements and agreements that our policy-making organs approved that allow us to provide our data for these purposes, but our mandate remains limited to treaty verification. Now, we provide, as Patrick mentioned, a capacity building program, and we provide software and training that allows national data centers to use our data for treaty verification. The reality is that that use of our data is very close to what they would do for seismic hazard monitoring, and so there is a benefit to being involved in treaty and the synergy between test ban treaty monitoring and the other use of our data for seismic hazard, for instance. But our mandate really is limited to test ban treaty monitoring. Do you want to add something?
Do we have more questions? Yes.
Thank you. My name is Tahir Akbaş from Turkey. I have a short question. Last year, there were some ruthenium measurement in European countries. Is there any involvement of the CTBT in that measurements or analysis? Thank you.
So we'll take a few more and then respond. No more questions? Yes.
Well, thank you very much for your informative presentation. Well, you've mentioned many civil and scientific applications of the IMS data. Well, and I wonder if this list is exhaustive. If not, can you say that in the nearest future, with new developments of the IMS system, there will be new applications, maybe new fields of its application, so that the whole system will be more appealing? Thank you.
Okay, so I will start and let Elena complement. Yeah, talking about radionuclide detections. We do have regular detections in the IMS network that we report constantly, and because there's a background at each station, but we see from time to time and radionuclides that are not necessarily typical of the background of an IMS station, and these are very sensitive stations, and therefore we do have regular detections, and we have episodes of detections at stations that are reported to national data centers, and national data centers get access to our data and products, and therefore any elevated concentration at that IMS station is reported. We've also some atmospheric transport modeling simulations that are made available to all our state signatories and national data centers. So we do see episodes of elevated concentration. On the second question about the list being exhaustive or not, that's an interesting question. The list is not exhaustive, and in fact the list is long and and we are discovering nearly and every day new potential applications of our data. What is interesting to note is also that the IMS now is becoming in a unique situation that we have been collecting at some of our stations more than 20 years of data, nearly continuously. So we have several decades of data available, which is an amazing source of information for people studying, for instance, climate issues and or train analysis. So it's a really important source of information, and we still don't know what will be found. And based on the analysis of several decades of data. But we did not mention today, but there are applications. We were amazed to see that people who are studying marine mammals recently found that using data from the hydroacoustic network, that there were marine mammals in some areas of the globe where they never thought they would find marine mammals before. So it's only by using data from the IMS. Another application, for instance, we did not mention is the use of, again, looking at the ocean, of the data that we have collected to contribute to the establishment of a noise limit in the ocean, a standard, and that was recently established for new projects being developed in the ocean, so that new project would not contribute to elevating the background noise, acoustic noise in the ocean, because this could be detrimental to the animals in the ocean. And people who worked on the elaboration of the standard used data from the IMS, because this was providing interesting benchmarks for their studies. So these are just examples, and we keep discovering, and more and more, either at global level but also at local level. So there are some phenomena about landslides, about other hazards that are of more interest in a particular localized area that can be really used and studied, and by using the IMS data. But Elena, you may want to complement.
Maybe just to make the connection to the next presentation after the break, which will be by our colleague Jolanta Kusmierczyk-Michulec, and somehow to underline that this is really a process. This development of civil applications is really a process that starts, that we support at every stage, and that starts with research institutes studying geophysical processes, using observations from the IMS network, using the vDEC, the Virtual Data Exploitation Platform, as a platform, and then as a next step, a new software or a new monitoring system is developed based on this theoretical knowledge, and eventually possibly it reaches a stage like for radionuclide emergency response or tsunami warning, where we then are mandated by our policy making organs to provide data to support such a civil application. So all these mechanisms are in place to support this process of going from a research idea all the way to an operational system. And the Science and Technology series of conferences plays a very important role in this process. And my colleague Jolanta will say more about this initial part of this whole process, which is the vDEC.
Thank you very much, Elena. Thank you very much, Patrick, for this very informative session. And as Elena just said, we will continue, in a sense, thematically with this in the next session, which deals with the vDEC, the Virtual Data Exploitation Center. That will be at 5 p.m., so we do have about a 20 or so minutes worth of break. There is tea and coffee available outside for those who need some sustenance. One thing I just want to mention at this point is that tomorrow morning the academic roundtable is the main session of the morning, and that will take place in conference room 2 on the 7th floor. It's a session that will be run, in a sense, by the academic community, but it's not restricted to members of the academic community. You're all, whether academics or not, very welcome to take part in that. Second item I want to mention is we have now finalized the sign-up sheets for the visit to the Atom Institute. So if you see your name listed on any of the sheets here on the doors, you are definitely going next Monday. If not, come and see me or my colleagues. Thank you. So, dear participants, we are now going to begin the final session of today, which follows on from, I think, many of the discussions we've already had about bringing in the scientific community, the academic community, and so on into the world of the CTBT. So, Jolanta Kusmierczyk-Michulec is going to present to us now on the Virtual Data Exploitation Center, which is a tool that provides scientists and researchers from all over the world and from many different disciplines with access to CTBT data to conduct research and to publish new findings. Jolanta, the floor is yours.
Thank you very much. So, good afternoon. As already was presented, I will give you some more details related to vDEC, which stands for Virtual Data Exploitation Center. During my brief presentation, it will not be long, I will explain how to apply for vDEC, what is needed, what kind of information you need to provide. I also will give some examples related to different technology, examples of vDEC projects. So it will give you an idea what other scientists, researchers do with our data. As you've seen this kind of map, it shows the distribution of all our different networks. So, as you already know, the International Monitoring System is a global system of monitoring stations using 4 complementary technologies: seismic, hydroacoustic, infrasound, and radionuclide. And on this map, you have different type of symbols which represent different networks, so like seismic, hydroacoustic, radionucleide, and infrasound. So as the main application of our data was already covered by my colleagues today, but CTBTO data are not only being used to detect nuclear explosions, but also to investigate the impact of, for example, climate change, warn about tsunami, or to track radiation on a global scale. So during the previous talk given by Elena, she already gave you the idea about civil application of our IMS data. The data can be also used by scientists. The only thing they need to sign a so-called zero-cost contract, which gives you access to our data, and that's vDEC. So, what is vDEC? vDEC is the Virtual Data Exploitation Center, and as was already mentioned a few times, it provides scientists and researchers from various countries with access to our data to conduct research. So they can get our data, they can try the idea, and they can publish their results. It's a zero-cost contract. It's a contract which doesn't contain any monetary remuneration between the parties for services or property, but contains legal requirements. And the easiest way to apply for vDEC contract is just to go to our website. Here is the address. So you just type www.ctbto.org and then go to specials, vDEC, and you get access to kind of a form. This is the snapshot of the vDEC online registration form, so you have to provide your data. And then when you submit this form, in response, you get email with attached template, which you need to fill, sign, and send back to us. And from that step, we will support you. So whenever you have question, you can ask us, and we will help you. So what do you need to know? This is this snapshot is part of from the vDEC template, and it includes the policy for provision of access to IMS data. And the important thing is that each contractor will access only those IMS data and IDC products necessary for fulfilling its task. So when you have an idea, you ask for a specific data set, you get access to this data set, but if you want to have access to other data, you need to ask for another project. The IMS data and IDC products will be used only for research associated with the development of the IMS and IDC or for the purposes stated in the contract. Access provided to an organization for the purposes of fulfilling a contract will terminate when the contract is completed. So it's important to note that each contract is for 2 years. So when you have a research project and it will take more than 2 years, you may ask again for, and you want to have access to our data, you may ask for the next projects, but each project is only for 2 years. And data access is provided only to a maximum of 3 individuals per contract, so it's also important to remember. So if there are more people from your institute which want to have access to our data, they may send us their own proposal, and there is no limit on the number of proposals per institution, but there is a limitation related to the number of users per project. The vDEC access credentials and the retrieved data may not be shared with others, so it's a kind of obvious. The restrictions placed on all users will not exclude the presentation of data or products. So we have this rule that if you have your project and you prepared, for example, publication, we ask to send us the draft version of your manuscript that we want to check. So it's a kind of a condition. You may publish the results, but we also ask not to publish the raw data, so it's in the contract. Also, you need to know that there is that each contractor has to sign a separate confidentiality agreement. So this is a kind of obligatory and is part of the vDEC contract. Here is some statistics. So this graph shows the number of vDEC contracts since 2011 per country. Since 2011, in total, we had 114 contracts, and they were signed by researchers representing 26 countries. As you see, in some cases, the number of contracts was larger. In some cases, was smaller. But still, it's a nice graph showing wide distribution of our data. In 2016, for example, a vDEC contract allowed scientists to participate in the second ATM challenge. ATM stands, as you know, for atmospheric transport modeling. Thanks to this contract, scientists could get access to emission data provided by ANSTO, and also they got access to xenon measurements, and we used those data to verify the results of our simulations. In total, 12 contracts were signed, so it was a very good use of the vDEC agreements. This graph shows the number of vDEC projects per technology. It is in percentage, so it's a contribution of vDEC projects for a given technology to the total number of projects. In red is indicated number of projects related to radionuclide technology and also ATM. The dark blue is hydroacoustic, the green is seismic, yellow is infrasound, and the light blue is mixed. And on the right side, there is an explanation what it means mixed. It's just different type of combinations of technology. So there is a combination of seismic and infrasound, hydroacoustic and seismic, hydroacoustic and infrasound, hydroacoustic, seismic and infrasound, seismic and radionuclide. So you have an idea how different technologies can be combined. But obviously it's not limited. So if you would like to apply for a vDEC project and you would like to combine different technology, it's still a place for it. Some more detailed examples. This is for hydroacoustics data. It turns out that one of the topics which was very popular is to use hydroacoustic data to study whales, and especially in the southern hemisphere, because there are no acoustic data from that region of such a temporal and spatial coverage. And since 2011, we had 10 vDEC projects related to this topic. Here on the right there is an image of such a blue whales. Some examples, hydroacoustic data were used to understand the inter-annual and seasonal occurrence of blue and fin whales at mid and low latitudes in the southern hemisphere. They were used to study the impact of, for example, shipping noise on them. But it's not limited. So hydroacoustic data were also used to study, for example, submarine volcanic activity, and also to investigate signal possibly caused by missing airliner. So there are only some examples of vDEC projects related to hydroacoustic data. There are many more. And I also extracted some examples of radionuclide data. We had several projects related to radionuclide, related to Fukushima accident. They were used, for example, to study atmospheric behavior, deposition, and budget of radioactive materials from the Fukushima nuclear power plant. They were also used to study long transport. We had projects related to beryllium-7. As you know, beryllium-7 is a very good environmental tracer. It can be used to study various atmospheric processes. Also, projects related to quantification of uncertainties in global atmospheric transport of radionuclides. So, a perfect example of the last application was this already mentioned by me, the second ATM challenge, in which 17 participants from 10 different countries participated. Among the countries were Australia, Austria, Germany, France, Canada, Sweden, Japan, USA, Great Britain, and Belgium. And the purpose of the second ATM challenge was to ascertain the level of agreement between the simulated concentrations and IMS measurements using only stack emission data and atmospheric model. Atmospheric transport model. So, as I already said, that it was a really good example of using the vDEC project to try to understand the uncertainties related to atmospheric transport modeling. Examples of seismic data. We have several projects related to DPRK, and because, as you already know, we had 6 tests. So each time we had after each test we had more people, more researchers who were interested to study, and we got projects related to the event. So they wanted to investigate characteristics and source depth of nuclear tests. So in 2006, 2009, 13, 16, and 17. But it's not the only aim of vDEC projects. The other, for example, topic is to discriminate between earthquakes and explosions near nuclear test site, to investigate the Earth's interior, or to study a tsunami. Some examples of infrasound data, how to apply. Researchers ask to study, they want to identify and characterize volcanic eruptions, to study thunderstorm activity, to investigate kernel-based machine learning techniques for infrasound classification. So the strong relationship between the scientific and technological community and the CTBTO helps to ensure that the IMS remains at the forefront of technological innovation and that no nuclear explosion goes undetected. And if you have any question related to vDEC, here is the vDEC email address, and our vDEC team will try to respond to your question. So that's the end of my presentation. So if you have any question, just the floor is yours.
Well, if there are no questions at this point and you want to consider in more detail questions you might want to ask, then once again feel free to gather them together and submit them through us to Jolanta. Jolanta, thank you very much for being here and joining us today to explain the vDEC. And that brings the third day of the symposium to a close. Tomorrow morning, we will be in conference room 2 on the 7th floor. That's where we will start with the academic forum at 9 a.m. Just to draw your attention to the fact that there will be a special event at 8:30 already in the same room tomorrow morning on the CTBTO Youth Group's newsroom publication. This is a special publication which is hot off the presses and which is going to be launched there tomorrow. For those early birds who will be in attendance, we will have tea and coffee at that stage. So have a pleasant evening and see you all tomorrow.